Hello students, Miss Slyman here, live from Istanbul, making your notes on angles in space. And so really here we're talking about angles between lines and planes and angles between planes and planes. So we'll start with lines and planes. So if a line is going to be parallel to a plane, then that means that the direction of the line has to be perpendicular to the normal of the plane. So in that case, of course, we would find that n dot m would have to be equal to 0. And then our line is parallel to our plane because the line is also perpendicular to the perpendicular of the plane. If a line is perpendicular to a plane, then we'll find that the normal to the plane and the direction of the line are parallel to each other. So in that case, n would be a scalar multiple of m. Okay, so when we talk about an angle between a line and a plane, we talk about the acute angle. We don't talk about the obtuse angle that is also formed. So if we think about what we know about planes, we always know the normal to the plane. So if we come down here, we've got the normal to the plane, which we've drawn here, or we could have drawn here. And thinking about this angle, it's a right angle. So our angle between the line and the plane, alpha, and theta, which is the angle between the direction of the line and the normal, theta and alpha are going to add up to be 90, and so we say that they're complementary. So complementary, of course, is summed to 90 degrees. So what we can do then is we can use our normal direction and we can use our m, dot those to find the cosine, and of course remember that cosine of an angle and sine of the complement are equal to each other. So let's think about that for a second. If we have a right triangle and this angle is alpha, that angle's theta, this angle's alpha. If we have, let's say x, y, z, so if you just think about this, cosine of theta is going to be x over z, which is the same as sine of alpha, also x over z. So that's what we're saying here, that sine alpha is equal to cos theta if they're complementary. If we do the dot product, like I was saying, we can find cos theta. But of course, knowing that the cos theta is the same as the sine alpha. And then to keep it all with the acute angle, we do the absolute value to find our acute angle. Okay, so find the angle between the lines and the planes. I didn't put the picture of this one in, sorry, but if you want to go look at it, feel free. So our direction of our line, looking at the equation of line, the direction of the line must be 0, 1, 3. Looking at our plane equation, remember we had that n dot r to r0 is equal to 0, where we're going from any point on the plane to a given point on the plane. Here we don't know the given point on the plane, but clearly our n value must be the coefficients of the x, y, z. So 2, 1, negative 1. And remember that comes from, it must be 2, 1, negative 1, dot with x minus x naught, y minus y naught, z minus z naught. So to get those coefficients in front of our x, y, z, those must be coming from the normal vector. And sorry, if I'm going to make this general, I should have labeled this like our a, b, c. Okay, so 2, 1, negative 1. So I'm going to find, first of all, I'm going to look at them, see that they're not multiples of each other, so we're not talking parallel, and I'm going to find the sine of the angle between the line and the plane, not the angle between the normal and the plane. Angle between the normal and the plane is with the dot product. So that's going to be absolute value of m dot n divided by length m times length n. And I'm going to pause this and figure it out, leave you to figure it out also, and come back and check. Okay, hopefully I did all my calculations correct. I got my alpha is about 15.0 degrees when I round to the nearest tenth, because we give degrees to the nearest tenth. All right, let's try another one. So here we have to look at our line in parametric form. Looking at our line in parametric form, I can see that its direction is -3, 1, 5. My normal vector to the plane is 2, 1, 1. Again, they're not multiples of each other, so we're not talking parallel. So I'm just going to repeat, sine alpha is going to be m, absolute value of m dot n, so -6 plus 1 plus 5. And already I can see that I've gotten to 0, so I'm not even going to calculate length m, length n. So I know that if I get 0 on top, that means that these two must have been perpendicular to each other, which makes me realize that what I've been saying in looking for these to be multiples of each other would mean that they're parallel, that the line would be perpendicular to the plane. But now, since the direction of the line, so let's think about this, our direction of our line goes in some direction m, and then we have our normal to the plane, we've gotten that those are perpendicular to each other. So now this must mean that actually our line is parallel to the plane. So line parallel to the plane. So now let's check and see if we have a point on our line. So we know a point on the line is 2, -2, 4. Let's see if that's on our plane. So is 2, -2, 4 on P2? So 2 times 2 minus 2 plus 4 plus 8, is that equal to 0? So we've got 8 plus 8 minus 2 definitely is not equal to 0. So not equal to 0, so we have that L is parallel, but not on plane 2. Okay, so again, if our direction of our line and the direction of the normal are perpendicular to each other, the line has to be parallel to the plane. Not what I was saying before. If they're multiples of each other, then the line is perpendicular to the plane. Okay, so this makes me, or this doesn't make me think, we're coming up to that later. So if we think about two planes can be parallel to each other, and they're going to be parallel to each other if their normals are parallel to each other. They're going to be the same if they also share points. Perpendicular to each other if their normals are perpendicular to each other. And if I think about the angle between two planes, well, the angle between two planes is the same as the angle between their normal vectors. And I want you to think about this conceptually. Maybe take a few pieces of paper, and because it's hard to see in this image, but think about whether this resonates with you as being true. That if I find the angle between the normals, I have also found the angle between the planes. Okay, so find the angles between the planes. So normal 1, normal 1 is 1, 0, -1. Normal 2, 2, 1, -1. And so I'm going to say that cos theta is n1 dot n2 divide by length n1, length n2. Pause to calculate. Okay, I got 54.7 degrees. And this is where you're really gonna have to think about, am I using cos theta or am I using sine alpha? But now I want the direction between these two, so I'm definitely using the cosine. And we're not looking at the absolute value either. All right. N1, 3, negative 1, 2, N2, 4, 2, negative 5, and repeat your process. So in repeating your process, maybe you found what I did, that I get 0. Well, if I get 0, that means that my normal vectors must be perpendicular to each other, which then means that my planes must be perpendicular to each other. So the angle between them is, of course, 90 degrees. Okay, so now we can think about intersections of lines and planes, and in our next video we'll look at intersections of planes and planes. But with a line and a plane, we can either the line can go through the plane intersecting once, the line can be parallel to the plane but not on it, and the line can be parallel to the plane and in it. So find the intersection between, here's our line and here's our plane. If I want to find the intersection between them, then I'm trying to say that this is a point on my line that lies within this plane. So if I put my line into parametric form, x is going to be 1 plus 4t, y is 3 plus 2t, z is negative 2 plus t. Now I'm going to plug those into my plane. So 2 times 1 plus 4t minus 3 times 3 plus 2t plus negative 2 plus t has to equal to 9. I just moved this over to the other side to give myself some space to write. All right, let's do some algebra. I'm going to pause. Hopefully you got a t value of 6. I can take that, plug it back in to get my x, y, and z. So 25, 15, 4 is my point of intersection between this line and this plane. Of course, you can always go back and check, make sure that this actually does work. So that would give us 50, let's just check it. So 50 minus 45 plus 4 minus 9 does equal 0. So this point is on both the line and it's on our plane. All right, find the intersection between this line and this plane. The other thing you might want to do is have a quick check to make sure that your line and your plane are not parallel to each other. So, because in that case we would have multiple points of intersection. But I think if we did end up having multiple points of intersection, we would end up getting that t could be any value. But let's just come on this one and have a quick check. So direction of the line, I'm going to switch colors. Direction of the line is 4, negative 1, 2. Direction of the normal is 1, 2, negative 1. And I'm just going to check that m dot n does not equal 0. So m dot n is going to be 4 minus 2 minus 2, and it does equal 0. This means that this is perpendicular, the direction of the line perpendicular to the perpendicular of the plane. Therefore, the line is parallel to the plane. So now we want to see if there's even one point on the line that's also on the plane, because then that would mean the line is in the plane and there's infinite points of intersection. So I'm going to take this point from my line and plug it into my plane to see if it's true. So 1 plus 6 minus 6, does that equal 0? Let's just see that I did that correctly. 1, 3 times 2 is 6, minus 6. Oh, I left off a 6. So when I plugged in the z, I had minus 6, and I also have minus 6. Does that equal 0? It does not equal 0. So that means that the line is parallel and not in the plane. So there is no points of intersection. Okay. There was a typo in your sheet here. I think it had a (z = 0, which of course is not the equation of the line. Here's our equation of our line, and here's our equation of our plane. So remember, direction of the line can be given by our denominators. So 3, -1, 1 is direction of the line. There's a point on the line that is at 2, -1, 0. Sorry, 2, +1, 0. The direction of the plane is 2, 6, 4. They are not multiples of each other. M dot n, let's see if it's equal to 0. 6 minus 6 plus 4, not equal to 0, so they should intersect at one point. So I'm going to come back and find my equation of my line in parametric form. So x is going to be equal to 3t plus 2. Y is going to be equal to -1t plus 1. And z is equal to t. I'm going to take those, plug them into the equation of the plane, because there should be a point on my plane. -1t plus 1 plus 4t, that already looks like a t, equals 10. So I'm going to pause and solve. I got a t value of 0. Let's see if that makes sense. That then is going to give us an x value of 2, a y value of 1, a z value of 0. Let's make sure that's on our plane. So that's going to give me 4 plus 6 is 10, minus 10 does equal 0. So here is my point on the plane. It's also on the line, and it is totally okay for t to be 0. I'm going to pause here because I have to head out to the airport to catch the flight back to Prague. So I'll come up with the second video, hopefully somewhere in the airport, or we're actually headed to the mall to go shopping, so maybe I'll find a cafe there.